Okay, right. So we are rolling. So this is week 7, lecture 2. In that sense that we just have one lecture this week. So we are now going to dive into the network layer. So I think this is a nice point to make that transition, because so far we've been discussing about things that happen in the end systems, right? If you recall, the application layer and the transport layer only work at the two end systems, and the core of the internet is kind of oblivious to the transport layer and application layer. So we are taking one step, we are sort of moving one step below in that protocol stack hierarchy. And as has been the trend throughout this course, we kind of will again look at some fundamental principles. So this will include discussions on the service model, this whole notion of forwarding versus routing. Today I'll talk a lot about IP addresses. And then, of course, how a lot of this is also instantiated in actual protocols, right? So the bulk of our discussion will, of course, be on the IP protocol. Next week, I'll quickly cover NAT and ICMP. So hold off for a little bit. So a little bit of background, going back to these discussions we've had earlier, how the internet originated in the late 60s. And a lot of it was largely funded through the defense agency in the US. So they had this DARPANET and ARPANET network set up. And around the mid 70s, new type of network started emerging. There was this person called Bob Metcalfe, who we'll briefly look at when we get into the link layer, who came up with Ethernet. There was this other bloke who came up with this whole concept of packet radio, and he set up a packet radio network in Hawaii. So essentially different types of networks started emerging, and what they found was this created isolated islands, and there was a need to sort of connect all these networks together. And in 1974, a very seminal paper on this, as the title suggests, a protocol for packet network intercommunication, was written by two gentlemen called Windsurf and Bob Kahn. You may have heard of Windsurf. He is widely regarded as the, I don't know, is it the father of the internet or the grandfather, whatever, right? So they came up with this whole concept of creating this IP layer, which essentially acts as a glue and allows us to connect different types of networks together, right? So you may recall this hourglass structure of the protocol stack, and how there's essentially just one network layer protocol, IP, which essentially glues the internet together. And an important component within or an important actor at the network layer is essentially these packet switches called routers, which are responsible for forwarding packets. So the routers are essentially the glue that connect all these networks together, and all these packets communicate using IP, which is a universal protocol. Below IP, we have various different kinds of link layer protocols. Above IP, we have different kinds of transport layer protocols, right? So IP is in that sense unique, that there's just one choice there at the network layer. So just a bit of context, what does the network layer provide? Well, it's running below the transport layer. So as you see there, the two endpoints, they generate the transport layer segments, be it TCP, be it UDP. On the sending side, the network layer will take this transport layer segment, create a datagram, add certain header fields, and then pass it on to the link layer below. And then at the layer 3, we call the packet as a datagram. So that datagram gets pushed through this network, reaches the next router. The router will then examine certain header fields in this IP datagram, and then make a decision where to send this packet to. And this keeps repeating at each router until eventually the packet arrives at the destination, where it can then just be pushed up to the receiving transport layer, right? So the network layer, as you saw there, is functioning in each and every device. So of course, we have the network layer on the end hosts, but more importantly, all the intermediate routers also implement the network layer, right? So the core function of the network layer effectively is to deliver these packets from the source to the destination through this maze of routers that make up the core internet. Now, there are two key functions of the network layer, and they're kind of different. They can seem to be the same, but they're actually rather different. So there's this function called forwarding. Now, when a packet arrives at a router's link, it needs to decide which outgoing link the packet should go to, right? Because in most of these pictures, you'll see that we draw very small topologies, but realistically, even in this small picture here, you see this router has 3 links, right? A practical router, particularly in the core of the internet, could have many more links, right? The order of tens of links. So the router needs to make a decision that, okay, a packet has arrived, which of these outgoing links it should send the incoming packet out to. Now, mind you, there's this term called port that's also used when we sometimes talk about the routers. Now, do not confuse this port with the port used here at the transport layer, right? Remember, we talked about sockets. So these port numbers here have no relationship with the ports when we talk about routers. I'll try to use links, but this is a very widely used terminology anywhere that you may read about routing. So just make sure you put this in context that when we're talking of routers, when we say a port, we basically mean this, the connection to the link, right? That's what we mean by a port. Okay, so forwarding is the process of moving a packet from one link to another. However, there's another function called routing, which actually determines the actual route, right? So this is a local action that's taken at one router when a packet arrives. But the question is, how does the router know where to send the packet, right? What is appropriate, essentially? What do we mean by the correct outgoing link? So this is actually determined by the routing algorithms. So there are routing protocols that are sort of running in parallel. And these routing protocols are executing on all routers. And as we'll see next week, together they figure out what would be a good route to be taken for packets going from one source to another particular destination, right? So a good analogy is essentially like when you're driving, right? So when you arrive at a particular intersection, you need to either go straight, make a left, make a right, or whatever, right? So that process is kind of like forwarding, because that's something you do at one specific intersection, whereas the actual route that you might plan, say you're going on a road trip, right? So you enter your starting location and location in whatever mapping application you may use, and it maps out the entire route for you. So that is effectively what we refer to as routing, right? And that's taken care of by routing algorithms. So routing algorithms, I'll do a quick overview now, but we'll discuss them in a lot more detail next week. So this is the specific interplay I was referring to, right? So each of these routers would have a routing algorithm running, and they would be communicating with each other, as we'll see next week. And based on certain control information they send each other, they can then create what's called a forwarding table. This forwarding table will have certain values, which, as you may have guessed, would be IP addresses, essentially. So when a packet arrives, a datagram arrives, the router looks up the destination IP address within this forwarding table. And when it gets a match, it will send the packet out on that particular link. Right? So this process of looking up the header within the forwarding table is referred to as forwarding, and then figuring out where the packet goes and pushing it out. But the way this forwarding table is actually populated is something that's done by the routing algorithm, right? They sort of work hand in hand. And just not stressing that forwarding is a local decision, whereas routing is something that is a global decision, and that all routers on the network participate in determining these optimal paths. So based on that, when we are studying networks, the general terminology we use is we refer to whatever happens on the critical path as a packet is being moved is referred to as the data plane, right? So this is basically what's done in forwarding. It's a per router function, and the goal is simply to figure out which outgoing link or which outgoing port the packet should go out to. The process that involves populating that forwarding table is what's referred to as the control plane. So this is again a network-wide logic, and the routers together figure out essentially what would be the good path to take from various source nodes to various destination nodes. And there are actually two ways to do that, which I'll briefly mention in the next slides. There's a question, does the input-output link correspond to a physical link? Yes, that is correct, James. So these are actual physical connections, right? So that's what we mean by links here. Okay, so two approaches. So the approach we'll study in this course is what we are seeing on this slide. So in this approach, we assume there's some routing process essentially executing on each of these routers. And based on certain logic, which we'll look at, each of these, the routing process will keep exchanging certain information with other routing processes on other routers in the network. And based on how they converge eventually, they will then populate a forwarding table. So forwarding tables will be populated in each of these routers. And then the data plane actions can take place. So this is what we'll be looking at in this course. And we'll look at the control plane next week. There's another approach which has also emerged, which is referred to as software-defined networking. So the idea here is to actually pull out some of this functionality and make it a little more centralized, in that there is this notion of a controller in a SDN network. The controller has a global map of this particular network, and then it can in a centralized manner decide what would be the good paths to take at each router, and it would create the forwarding table centrally and then simply push these out onto an agent that's executing on each of the routers, right? But since we are sort of limited on time, I won't be covering SDN in this course because something has to give. I can't cover each and every aspect of networks here, right? Okay, so in terms of the service model, things are pretty straightforward, right? So this is something we also discussed when we talked about the transport layer, because at the transport layer, since it's running on top of the network layer, we need some understanding of what the network layer provides. And as we already discussed, the network layer of the internet is not really providing you much. It's just follows what's called a best effort service model, in that it tries its best to deliver the datagrams from the sender to the receiver, but it does not give you any guarantees. So it does not even guarantee that the datagrams are actually delivered. So there is no guarantees of reliability, right? And that's the reason we saw that TCP has to implement a reasonably complex mechanism in order to provide the abstraction of a reliable byte stream, right? The network layer of the internet also does not guarantee timing, in that there's no guarantee that first of all, there's no guarantee that the datagram will reach the other side. But then if it does reach, there is no guarantee on when it will reach. There is no guarantee on the order of delivery, which means if two packets are sent back to back, there is no guarantee that they will arrive in that same order, right? So packets may get reordered as they make their way through the internet. And there is also no guarantee of any bandwidth on an end-to-end basis, right? So you might wonder if its best effort is not guaranteed anything, how come we are still using that, right? Because if you may think about it, a lot of us are now using a fair amount of multimedia applications, like this very lecture is being streamed, right, to you over a sort of, and this is sort of a live streaming we are talking about, right, with a very minute delay, I presume. So how does this work? Well, it's just simple, right? I mean, the whole point of having this best effort model has allowed us to simplify the routers. So the routers can exclusively focus on forwarding packets as fast as they can, which helps allows them to at least provides some notion of low latencies. One way to tackle congestion issues is to over provision the network. So a lot of networks these days are highly over provisioned. By over provisioning, I mean they are sort of try to install sufficient bandwidth that they can handle most typical peak duration traffic, right? So there's enough bandwidth available to allow all sorts of real-time applications to work, right? Of course, occasionally you might have some transient overloading issues and potentially some queuing and some packet loss, but it goes away in most cases. It doesn't sort of remain sustained, right? And then this whole notion of coming up with this data centers and content distribution networks, where we sort of are relying on these entities to get the content closer to the clients, and coming up with nice mechanisms where they can distribute this very quickly to the requesting clients, right? And in particular, hosting this at multiple places, just replicating the content again and again, right? Because in the end, storage is relatively cheap these days. So all of this has essentially allowed us to still rely on this best effort service, and hence there's no real need to change that, right? And so that's why this simple model has still survived, and we generally don't have big problems with the internet. Okay, so let's now start looking at the IP protocol itself, and we'll start off by looking at the format of the protocol. But before that, just a little bit of context about what's happening at the transport layer. So you may recall on the top, we have the various transport layers. Here we are currently sitting at the network layer. Below us, we have different link layers, right? Then, as we already discussed, we have the control plane, which is implemented in the form of routing protocols, which we'll look at next week. And these routing protocols create these forwarding tables, which make up the data plane, right? Then we have, of course, the IP protocol itself, which defines the format of the datagram, which defines how IP addressing is handled, the various packet handling conventions. And there's a separate protocol that takes care of error reporting and allows routers to sort of signal other routers. So this is called ICMP, the Internet Control Management Protocol, which we'll briefly look at next week. In fact, you have already got exposure to ICMP. You've used ping and traceroute, which actually make use of ICMP. So we'll briefly look at that next week. So let's start by looking at the datagram format, and we'll walk through this and explain the various, the semantics of the various fields, right? So first up, we'll focus on the fields for reading the packet correctly. So those are the three fields that you see circled. So the first field is the version. So this indicates what version of IP protocol is used. So today's discussion will exclusively focus on IPv4. I'll briefly talk about version 6 next week, right? So this is basically the number, the version. So the receiving router knows which IP protocol it is, because the packet formats are different for IPv4 and IPv6, right? There's a question, what happened to 5? I don't know really what happened to 5. There must be some history. How they skipped 5. I'm not sure. There's a question, so does ICMP cut out the transport layer? That is, the application layer interacts directly with the network layer. You could say that in that ICMP itself runs on top of IP, if you may. So an ICMP message is encapsulated in an IP datagram. And certainly when you're sending ICMP messages, you're not using either TCP or UDP, right? So traceroute, remember that's it's implemented in your operating system in a sense. So yeah, it does bypass, if you can say that, the transport layer, because it's directly sending ICMP. What's an IP datagram? Well, an IP, if you recall, at different layers, we call a packet differently. So at the transport layer, a packet is called a segment. At the network layer, a packet is called a datagram. Okay, so that's the version. Then we have the length of the header. So this is again very similar to TCP and UDP, where because the header is not fixed, there's a option field, which means we need to indicate how many bytes make up the header. So the router knows that, okay, this is the header, right? So the header is specified as a multiple of 32-bit words. So the typical header, if you disregard the options, is 20 bytes. So all of this makes up 20 bytes. So if you disregard options, as we'll normally the normal size of the header would be 20 bytes, which is denoted as 5, because the value there is a multiple of 4 bytes, essentially. Then we have the total length of the IP datagram. So this is the total length. It includes the header and the payload. Now there are 16 bits. So technically you can have a maximum IP datagram of that size, but we've already discussed about the MTU, the maximum transmission unit, that is imposed by the link layer protocol. So very rarely will you see actual datagrams of that size, because almost all link layers will have smaller MTU values than that. Next, we have the 2 fields for reaching the destination and allowing the destination to know where this datagram came from. So that's the source and the destination IP addresses, right? And we'll look at IP addresses later. Next, we have a field for multiplexing. So once the datagram reaches the destination, what should the destination do, right? Because remember, the destination might have various TCP sockets, various UDP sockets. As we'll later see, ICMP also runs directly on top of IP. Some of the routing protocols also run on top of IP. So there's a routing protocol called RIP, for example, right? So when a packet arrives at the destination, it needs to know where it should send it, right? Should it be sending it to TCP? Should it be sending it to UDP? Should it be sending it to ICMP or some routing protocol? So this is effectively demultiplexing. If you may recall, that's what all is also done at the transport layer when you're demultiplexing to an actual process, but the same thing needs to happen here. So there are specific values that are used for these protocols. So TCP has a I forget the exact number, but TCP has a specific value, UDP has a specific value, ICMP will have a specific value, and so on and so forth, right? So that's the 8-bit protocol field, which is used at the destination. Next, we have fields to do with some problems that might happen in the network. So these 3 fields here are for fragmentation, which I'll talk briefly. And then here we have something called the time to live, and then the checksum. So what could be potential problems that are relevant at the network layer? Well, one is looping, right? Effectively, sometimes, I mean, of course, this doesn't happen all the time, but sometimes there are some problems in the routing protocol. and inadvertently, there could be transient loops, right? So you might have a situation where this router sends a packet here, this router sends it back here, this sends it here, and this sends it back here due to some problems in the way the routing protocols were implemented. Now, we don't want packets to keep bouncing around in the network forever, right? Because it's highly wasteful. It's very likely that if this packet has been bouncing like this, the application that sent the packet very likely would have retransmitted. For example, if it was a TCP packet, it would have already been retransmitted due to a timeout or whatever, right? In any case, we don't want such old packets to keep bouncing around and heading nowhere, right? So the way to prevent that is to have a certain time to live field in the IP datagram. And this field is actually decremented at each router. So each time a router forwards a packet, it decrements the value in the TTL by 1. Now, eventually, if it so happens that a packet arrives at a router and the TTL value is, when it decrements it, it becomes 0, it means this is too old. This datagram is now too old, and the packet will actually drop this. The router will drop this packet because it's too old, and it will send back a control message, an ICMP message to the source IP address, indicating that this time exceeded. So there's a special ICMP. ICMP packets are essentially, they have these codes. The code indicates what type of error it is. So it will send a particular code back to the source indicating that this packet was dropped because the time exceeded, right? So that's how the TTL is used effectively to sort of prevent packets from just staying in the network forever. Now, there are various different recommendations on what should be the default value. So this is I mean, it says here the recommended default is 64, but again, it's very implementation specific. Some could use higher, some could use lower values, right? Does the router reduce the TTL? Yeah, I think I said that, right? That each time a router forwards a datagram, it reduces the TTL by 1, essentially. What causes looping? Well, I just indicated again that there could be problems in the routing protocol, right? Sometimes there can be misconfigurations. And yeah, I mean, eventually they do get detected and corrected, but for a transient period, you might have some misconfiguration, right? Could a malicious user send lots of packets with very high TTL to deliberately consume? Yeah, fair enough. That's a good point, Daniel. So you could, though these days, most networks will also be running some sort of firewalls. They will be monitoring the load on the network. And then if they detect that there's too much, let's say there's one user here and he's constantly putting out packets, right? Your ISP might do some metering. And if they check your packets and if they find something unusual, like you're sending packets with very high TTLs, for example, then they may simply block your traffic, right? So in theory, yes, some of these attacks could be possible. In practice, most of these attacks have already been launched. So the system designers now put in all sorts of checks to prevent those attacks, right? Okay, so the next thing is, okay, what if the packet itself is corrupted? So now note that most of the packets, not all, but certainly most packets carried inside an IP datagram will be either TCP or UDP segments. And as we already discussed in TCP, UDP, there is already a checksum, right? So that checksum takes care of the actual payload within the IP datagram. If you go back here, this is the payload, right? So if this is either TCP or UDP, right? So this is already covered by checksum, by the TCP or UDP checksum. So assuming that if there are any potential bit errors, really we only need to focus on the headers, right? So that was the logic when they designed the IP protocol, that they thought it wasteful to again include this, the payload itself for checking errors. So they only focus on the headers, right? So the actual algorithm is exactly the same as TCP UDP. So I won't repeat that algorithm, but it's only computed over the packet headers. And so when a packet arrives, a datagram arrives at a router, it first runs the checksum algorithm. If it detects that the checksum is erroneous, it will simply discard the packet, right? And that's it. I think that it might generate an ICMP message as well. We can have a look at that when we talk about ICMP. But it's likely that it will send an ICMP message back to the source saying the packet was dropped because of a checksum error, right? Because there's no point forwarding a packet through the network if we know it has bit errors, right? It's wasteful. Now, one thing to note here is that the router will have to recompute the checksum for that datagram when it forwards it. Now, you might wonder why. Well, as we already noted here, the router needs to decrement the TTL, right? Each router has to decrement the TTL by 1, which means it's changing certain information in the header fields, which means the checksum will no longer match, right? Because something has changed. So each router has to recompute the checksum every time, right? Now, clearly that creates a little more effort on the routers to do that. So you might say, okay, why not exclude the TTL, right? Because if this is the case, each router has to do it. So why not exclude the TTL? I think the argument they made at that time was, well, the router is itself going to change the TTL. So the likelihood that it might introduce an error while changing the TTL is reasonable to warrant it to compute the checksum again, right? So they sort of looked at the trade-offs and they said, hey, if the router is actually going to change that field, it's possible that it might introduce some errors in that field, right? So that's the reason they said, okay, let's recompute the checksum over the entire header and not exclude the TTL. And then why only header? Well, we already discussed this because most of the payload is either UDP or TCP, and we already have the checksum for that. So there's no need to again recompute the checksum over that. Right? Okay, the next thing to look at is what's referred to as a fragmentation. So let me first explain what's going on here. So remember that as a packet makes its way through the network, the link layer, because it's moving across various links, so the link layers could actually change, right? So here, for example, you might have Ethernet. This might be what's called a sonnet link, maybe here there's Wi-Fi. So essentially, as the packet makes its way along different hops, then it's going to be passed over different links, different link layers, and each of those link layers may have a different maximum transmission unit, the largest size of the packet that it can actually transmit. So you might have a scenario where, let's say, a datagram comes in at that router. It looks up the forwarding table. It decides to forward it here. And now the MTU of this link is smaller than the MTU of this link, right? Which means we cannot send this datagram as one datagram. So what does this router do, right? It can't sit and cry. It needs to do something. So the designers of IP said, okay, what we'll do is we'll allow this route, since, I mean, what were the options? Well, they could have told the source, hey, this is too large. Can you reduce your packet size to this? But that's perhaps a little wasteful having to do that. So they said, okay, if we do encounter that situation, let this router then break it up into smaller fragments, depending on whatever the MTU is here. Right? So this is referred to as fragmentation. So depending on the size, I haven't given you numbers, but let's just say in this example, this datagram gets split into 3 smaller fragments, and then those 3 fragments make their way through the network. Now note that each of those fragments is still a well-formed IP packet. So it still has a regular IP header, right? And we'll look at exactly how this fragmentation happens in the next slide. But one point to note again is now who does the reassembly, right? So the question again was, okay, if we are sending these fragments, should they then be reassembled here, right? And then this router can then forward the larger fragment. Or should they be reassembled right at the destination? Now, the way IP is designed is the reassembly happens only at the destination. Can one of you think of why? What are the downsides of requiring this router to do the reassembly? What could be the potential problems? Why did they not choose that approach and instead decided to do the reassembly at the destination? Yeah, I think some of the points you're all making are spot on. So the problem, one immediate thing that comes to mind is, okay, you recreate this large packet, and then what if later down here, again, you need to split it up, right? Because again, this packet is too large to be sent out on this layer, right? So we have wasted effort trying to reassemble a packet here, and then wasted effort to again break it down here, right? So that's one of the primary reasons they said, okay, let's just leave those fragments as they are and reassemble them when they get to the destination. Now, clearly, as you may realize, in order for the recipient to actually line up these packets correctly, because remember, again, just because fragment 1 was sent before 2 was sent before 3 doesn't mean they'll arrive in that same order, right? Fragment 3 might arrive before 2 because it might take different paths. So we need to add certain information in the headers so that the recipient can then align them correctly and combine them, right? And in fact, the recipient should also know it has received all the fragments, because how would it know that there are 3 fragments and not 4 and not 2, right? So we need to add certain information in those headers to allow the destination to do the reassembly, right? There's a question, does the destination router have a buffer to store the smaller datagrams? Yes, so that would be typical, right? So when this destination receives a IP datagram, it can look in the header, and as we'll see in the next slide, certain fields in the header will tell it that this is a fragment. So it will then wait for the other fragments to arrive and then combine it to form the original datagram. So let's look at an example. So let's say we have a 4,000 byte datagram, right? An original datagram that has arrived at a router, and the outgoing link has a MTU of 1500 bytes. So clearly this doesn't fit in this. And if you do the math, you'll see this requires 3 datagrams, right? 3 smaller fragments essentially. So we know that we need to split this up into 3. Obviously, the first 2 will be the full size packets, and whatever is left behind will be stored in the last fragment, right? So there are those 3 fields that you saw that are used. So the first one is an ID field. So this is just an identifier. So the source creates this identifier. It's probably just some random number generation that's used to create that. So this identifier is simply copied over into all the fragments. So this allows the recipient to know that all of these fragments belong to the same original packet because their IDs are the same. Next, we have what's called a MF flag. So this is what's called a more fragmentation flag. So this is set to 1 for all fragments except the last. So again, the recipient, when it sees all these fragments, it needs to wait for a fragment that has this flag set to 0 in order to know that it has now received all the fragments. So that tells it it's the end. That's the last fragment, right? So it's an identifier for essentially the last fragment. Then we have something called the offset. So the offset indicates the order of the actual data, right? So this allows the recipient to line up these fragments together. So the offset is expressed as a multiple of 8 bytes, right? So let's look at some simple math here. So the original data was 400, the datagram was 400 bytes, right? And remember the IP header itself is 20. So the actual payload here is 3980, right? So the total payload of this IP datagram is 3980. Now we know that these smaller fragments can be up to, and in fact, the first two are 1500 bytes. So they will actually contain 1480 bytes because 20 bytes again make up the headers. So the first two fragments contain 1480 bytes, and the last fragment will contain whatever is left behind. So essentially add these two and subtract from that. So that gives us 1020. Now the offset that you see there is a multiple of 8. So it's basically telling how much the payload is offset from the start of that original datagram, right? So since this is the first fragment, of course, the offset will be 0 because that is the starting fragment. Since this is the second fragment and it's offset by 1480 bytes, we take 1480 divided by 8. So the offset value is 185. This third fragment is offset by 1480 plus 2, right? Because that's what the first two fragments contain. So the offset that you see here is that basically, right? So it's offset by 370 times 8 bytes, right? So that's how the fragments are actually created. Right? There's a question, why not use sequence numbers? If you're referring to TCP, well, remember IP datagrams could carry anything, right? You can't assume that it will always be a TCP segment. And as Tim has already indicated, you want a clear separation between things done at the network layer and the transport layer, right? We want to keep all of these layers independent as much as possible. Okay, so the procedure is there's a question, 13-bit fragment offset in the header. Not sure what you mean by 13-bit. The offset is how many bits? Oh, yeah, you're right. Yeah. So yeah, that's essentially the offset. Could offset be decimal? I'm not sure what you mean by decimal. It's a multiple of 8, right? As I already indicated. So yeah, of course, it's a decimal value, but it's expressed as a multiple of 8, as you saw here. Right? So fundamentally, then will all datagrams be multiple of 8? Yeah. So essentially, if it's not a multiple of 8, I mean, remember the last, this last, whatever is left here, right? It doesn't have to be a multiple of 8. So in that sense, it doesn't matter, right? Basically, it's whatever is left behind. For example, if 1019 was left behind, that would still be okay because this last, there is nothing after it, right? So it should be okay. Why do we need to be divided by 8? Well, I think that's because the way this field is used, I think they've thought if we were to support, if you recall the IP, the length is an IP packet could potentially be of that size, right? So I think this 13 bits would not have been enough to fit those offsets if you really had those very large packets. So I think if you do the math, you'll see that this won't be sufficient to fit very large offsets. So I think that's why they chose that to be a multiple of 8. Right. Yeah, and typically, as some of you are pointing, most MTUs tend to be a multiple of 8 anyway. So this tends to be a non-issue really, right? And even if it is, it's a minor adjustment that needs to be made, right? You might have for example, if this packet was not a multiple of 8, you would then reduce the amount of data here slightly to make it a multiple of 8. That's all. Right? So it's a minor adjustment. So the way fragmentation works is it first needs to decide how to break it up. Then it copies certain IP headers to the pieces, basically that ID field. Then it sets the flags. Essentially, all flags except the last will be set to 1. It will put in the offsets correctly. It will have to recompute the checksums, right? So that's all that's done at the sender. And then the recipient will essentially line all of them up and then extract those payloads and form the original IP datagram, right? Now this again, it's probably not typical, but it can happen, right? Sometimes you may end up where a fragment itself needs to be fragmented, right? So this is just an example I've given you. So here is the original datagram that was fragmented into these 3 fragments. The MTU is say 1420 here. Now it so happens that this fragment 2 went along a path where one of the link layers couldn't even fit in 1420. It had an MTU of 820, right? So you'll notice here this second fragment is also fragmented further, right? So essentially here the offset for the first one here, the offset is not 0. It stays whatever was the original offset. And then this one will be offset by 100 because this can fit 800 bytes in the header. So 800 by 10 is 100. So 175 plus 100 is 275, right? So this can happen. Again, it's a hypothetical scenario. It may or may not happen. It really depends on the specific link layers in use, right? Okay, so clearly you see there are some problems here, right? This fragmentation, I mean, it solves a problem, but it's still quite fiddly, right? So there is actually a way for 2 endpoints that are communicating to discover the MTU along the path, whereby by doing this discovery, the source can then start using sizes that do not need to be fragmented along the path, right? So for example, again, a hypothetical network like that, the first link has a MTU 1400, this has 1200, this has 900. So there is a specific protocol called path MTU discovery process. So in this, what happens is the source will send a packet of a particular size to test all the routers along the path towards the destination to see if these routers can support this particular size of MTU. And it does that by setting what's called a do not fragment flag. So if you go back to the header, you'll see there are 3 bits which are referred to as flags. So one of them is called DF flag, right? So which means any router, if it can't fit this packet on the outgoing link, should not fragment it, but should send an error message back. This error message is essentially an ICMP message that goes back, right? So what the source can do is it can try, say, 1200. If this, it first tries 1400 because that's the MTU it has. This router can only fit 1200. So it sends back an ICMP message saying try 1200. Then it tries 1200. It goes through here. This router cannot fit that in here. So it sends back a control message saying try 900, right? And then this can try 900. No error messages are received. So from that point on, it can always use 900 so that there's no issue of fragmentation, right? So this can be used to avoid all this fragmentation. Right? Now, of course, there's no guarantee that this path will always be maintained, right? Because again, remember, the internet doesn't give us guarantees on the path. So as one of you pointed out, sure, there is no guarantee that all packets will necessarily take those paths. So what could be done then is, let's say initially we agreed on 900. So it keeps sending packets of 900. Now, if somewhere along the way the path changes, right? Let's say the path changes to another path this way and the MTU there is 800, again, hypothetically. So suddenly it will start seeing that packets are being fragmented, or it might still set the DF flag whereby it generates a error message, right? Or it might keep trying to repeat this process every 10 minutes, every 15 minutes or something like that. So some heuristics can be employed whereby you can retry this discovery process every few minutes just to see if paths have changed or something like that. There's also a question about ICMP messages being blocked. Yes, that is true. Though in most core routers, you'll see that they're not, I mean, again, typically, and it's not guaranteed, but most of the drops that you saw were happening in the destination network, not so much in the core network, right? So when your packet reaches inside the destination network, that's when they start dropping. Right? So usually the core routers will not necessarily drop ICMP packets because they do need to communicate some of these errors back to the source, right? So typically, but again, no guarantees. Yes, certainly sometimes even core routers may start dropping or prevent, not allow routers to send back ICMP messages. Why do applications want to prevent datagram splitting? Well, because it's fiddly, right? I mean, it's not so much the application. If you think about it, a router has to spend extra work to do this, right? Every time it needs to create a fragment, you're taking away time from it processing the packet quickly. And remember, these core routers are handling gigabits, terabits, zetabits of traffic, right? So ideally, you do not want them to waste time doing fragmentation. It's not so much the application, it's generally for the health of the network. You do not want, and in fact, you'll see that in IPv6, they've done away with fragmentation. So in IPv6, if you end up in a scenario like this, a control message is simply sent, indicating the packet is too large. So in IPv6, this router will not fragment anymore, right? And there are all sorts of attacks that could also be launched. I haven't covered that, but you may imagine you could start sending all these fake fragments unnecessarily and create havoc, right? So lots of issues with fragmentation, so it's not generally preferred. Okay, so what next? The special handling. So there was this header called type of service. So when the IP protocol was designed, they thought, okay, we might give priority to certain types of traffic, create, for example, if it's a multimedia traffic, we give it high priority over, say, an email packet. But this is largely not followed. So even though they have this field, it is very rarely used. So we'll kind of skip over that. And there are certainly some options, like you could specify your desire to go through certain specific routers and stuff like that. But again, options are very rarely used these days because again, it adds extra work for the routers, right? And in fact, IPv6 also does away with options. So yeah, so just to recap, here is again a look at the headers. And I'll leave this slide here for a minute while I quickly see if there's any questions. Has anyone studied network health in terms of not moving the transport checksum up to the network layer? More work with processing packet, but less work. I'm not quite clear what you mean by not moving the transport checksum. Okay, if you mean the checksum, if I again recall correctly, which we'll look at again next week, IPv6 also does away with checksum. So it's no longer doing checksum at the network layer. So that I mean, as you see, IPv4 it dates back to the 70s, right? So clearly some of the things that were envisioned then are perhaps not the best things to do for the general health of the internet. So in IPv6, you see they've streamlined a lot of this. So there's no fragmentation. I believe there's no checksum as well in IPv6, right? are the type of service not used as in not implemented on routers, or just that end systems don't usually encode them? I think it's both. So it's not normally encoded at the source, and it's not normally used at the routers. So it's kind of defunct in a sense. So typically, if you look at the headers, excluding all the options, we've already seen that with TCP, we have 20 bytes, with UDP, it's 8, and then IP adds 20 bytes. So assuming it's TCP IP, so far we have 40 bytes of headers, and then any headers within the application layer itself. And then the link layer will also add its own headers, right? So there's a fair amount of headers being introduced as the packet moves through the network. Okay, so I think this is a good point to take a break. Oh, I actually forgot to put up a meme for today. Sorry about that. I'll make it up. I'll show you 2 memes next time. So yeah, let's have a short break. And I'll be back in 3-4 minutes. I'll pause the recording. Till then, recording. Right. So let's now jump into addressing, IP addressing. So as you may already have realized, and as we've discussed earlier, every device that's connected to the internet is assigned a unique 32-bit identifier. Now, precisely speaking, it is not every device, but it's actually every network interface. So essentially any connection, wired or wireless, that's coming into your device would be assigned a unique IP address. Now, for the moment, I know someone might ask me about network address translation and private IP addresses. Let's hold on to that till the next lecture. For now, let's just assume IP addresses are globally unique, right? Because that is not entirely true. So we'll just, for now, abstract over that and come back to that when we talk about NAT next week. So by interface here, we mean any actual connection between the host router and if link. I mean, strictly speaking, it doesn't have to be a physical link as such. It could be a wireless link as well, right? Now, of course, routers will have multiple interfaces. I mean, even a simple router like this has 3 interfaces. Core routers will have many more interfaces, but even hosts typically have 1 or 2 interfaces, right? So for example, right now on this machine, I have a wired Ethernet. I've also got a wireless inbuilt card here, right? So currently my machine is connected to 2 networks, and each interface would be given a separate unique IP address. The format to represent an IP address is as you see there on this picture. We break up the 32 bits into 4 blocks, each of 8 bits. Essentially, each is a byte. And then we convert each of those to the decimal notation, and then we put a dot, right? So that's the standard way to define IP addresses. Now, the question is, how are the interfaces actually connected? So again, since we are currently focusing on the network layer, we don't really care about that in this discussion, but we'll certainly look at that in the link layer. But just for a quick preview, the typical option with a wired network is to have an Ethernet switch, like you see here, and then you have the Ethernet cable running from your machine to the Ethernet switch, right? So this is kind of like a star topology as you see it here. The other typical option is, of course, to use a wireless access point, which would be connected through to a router like that, through a wired, likely wire. I mean, even, yeah, this will very likely be a wired link. Another option could also be a cellular network if you've got a adapter that's a 4G or 5G adapter, for example, right? Which would be similar, except that would be a base station and you would have larger coverage area than say an access point. So we'll look at some of this a little later in this course, but for now we kind of abstract over the link layer stuff. And now we move forward to another important notion, which is referred to as a subnet, right? So what is a subnet? Well, basically, if any device on a network can communicate directly with any other device without having to go through a router, then those two devices are considered to be, all those devices are considered to be part of the same subnet. So effectively anything behind a router, like this whole network that's behind this router link, this whole network, and this whole network, right? So in this example, we have three subnets. And the way IP addresses are assigned has some meaning. So you don't sort of randomly assign IP addresses. So here you're already seeing a pattern, right? If you look at all these IP addresses, you'll see the first 24 bits are actually the same, 223.1.1, right? So, and the same applies here, .2, 1.2, 1.2, 1.3, 1.3. So hopefully you're starting to see a pattern there, right? That certain number of bits are the same for all the devices that are on this same subnet, right? And a certain number of bits to change. So effectively the IP address is just like your postal address, right? When you write a postal address, you have the number, the street name, the suburb, the state, and then the zip code, right? PIN code. So similarly, IP addresses also have a structure. So the highest sort of the leading bits, essentially, certain number of those leading bits or higher order bits are common, and that's referred to as the network part or the subnet part, and the remaining lower order bits are referred to as the host part. So effectively, you're going from left to right. So the left certain number of bits, in this example, these are the first 24 bits. So those are referred to as the subnet part. So the way to identify a subnet really is, as it says there, you detach essentially each interface from its host or router, creating effectively an island. So these blue parts that you see here are those islands, right? Now, of course, this interface and this interface cannot communicate with each other without going through a router. So they're clearly not part of the same subnet, right? Whereas this and this, this and this, this and this, and any combination of those will be part of the same subnet, right? So each of those networks is called a subnet. And in this example, the first 24 bits of the IP address are the same for all devices on that subnet. So on this subnet, it's those 24 bits. On that subnet, it's that. And then on this subnet, it's these, right? So the way to represent this, which we'll again come back to in one of the later slides, is to use this slash notation. So when you're sort of talking about an IP address for a block of IP addresses that's assigned to a subnet, we normally use this a.b.c.d/x, where x indicates the number of higher order bits that are the same for all devices that are on that network. So that's effectively defining the network part of the address, right? How is the hierarchy defined? So Tim, I'll come back to that. I have some because otherwise it will require me to jump ahead quite a bit. So I do have some discussion on those hierarchies. Essentially, it goes back to how the internet is structured, right? So you have this larger ISP gets a block of IP addresses, and then let's say UNSW gets a part of that IP address block from, say, ARNet, right? And then within UNSW, again, we assign a block of IP addresses to engineering, a block of IP addresses to medicine, and so on and so forth. So it's effectively you're creating these sub blocks within each other, right? So we'll come to that in just a few minutes. So effectively, moving to this slightly more complicated example than before, what are the different subnets here, right? So in fact, I've answered this. I perhaps shouldn't have asked you, but hopefully you're seeing those islands, right? So there are 6 subnets here. So like before, this is one subnet, this is one subnet, this is one subnet. So that's easy. But then if you look at these 2 interfaces, right? So they can connect to each other without having to go through a router, but then this cannot communicate with this without having to go through a router, right? So that's the reason this is a separate subnet, this is a separate subnet, this is a separate subnet, right? So again, the same idea, you detach those hosts and you see, focus on these isolated islands, and each of them now becomes a subnet. And in this example, we are assuming that the first 24 bits of the addresses are the same for all interfaces that belong to each subnet. So for example, if you look here, the first 24 bits, 223.1.1 are the same, right? Similarly here, 223.1.9 is the same. So the way to represent that would be like that, right? So /24 indicates the first 24 bits of this address are the same for this subnet, and then the remaining 8 bits would be different, right? So hopefully that answers that question about the slash. So this, so for us users, right, as humans, it's easy for us to sort of remember this way, that essentially we have a certain number of bits that make up the network part, and then the remaining bits become the what are referred to as the host part. But again, remember, routers are better at doing bitwise arithmetic. All computers are better at doing bitwise arithmetic. So there's something, another way to represent how many bits make up the network part and how many make up the host part is what's referred to as a network mask, right? So essentially the way the mask is used is any device is given an IP address, and as you'll see later, when it is acquiring this IP address from what's called a DHCP server, it also obtains what's called a network mask, right? So by doing a bitwise multiplication of these two, the device can figure out how many bits essentially make up the network part and how many make up the host part. So in other words, let's look at this concrete example. So this refers to that host B, right? So let's say this host B has been given that address. It has been told this is the mask for this entire subnet that it belongs to. So what this device can do is it can convert all of this to binary, like you see here, and then do a bitwise multiplication essentially of these two, right? So you notice here there's this string of ones, right? So effectively, when you do a bitwise multiplication, all of these first 24 bits will essentially remain as they are, as the original IP address. And then whatever is 0 effectively becomes 0, right? So when you do a bitwise multiplication, whatever remains is essentially the network part, right? So this is essentially the network part. So this tells this machine that any other device that's on this network will have that as the network part. In this case, it's the first 24 bits. It doesn't have to be 24, mind you. This is just an example. Okay, as you'll see later, the /x, the x can be variable essentially. X doesn't have to be 24. It can be 23. It can be 21. It can be 25, right? And then whatever remains, essentially, if you do the subtraction, if you subtract the network part from the IP address, whatever is left behind becomes the host part effectively, right? Why does the host want to know that? So again, this will become a little more apparent later. So when a host is sending a packet to a particular IP datagram, a destination, right? So the first thing, let's say this host B wants to send a packet to another host A here, right? So the first thing the host would do is it would know A as an IP address. So it would then, and it would know its subnet mask. So it will do this math to first check if A belongs to this same subnet or A belongs to a different subnet. If A belongs to the same subnet, it doesn't need to send the packet to the router because it means the destination is on the same network. If A belongs to a different subnet, then this will have to send it to the router and then the router will forward it, right? So that's the reason a host needs to know its own mask so that for any destination, it can then check if the destination is on the same subnet or on a different subnet. So we'll talk a little bit about that later. I'm just jumping ahead a little bit since you asked the question. Right. Why not ignore the last part to get the network part? Well, that's exactly what the mask does. I mean, how this is another way of telling your network that the first 24 bits make up the network part, right? So this is the way to communicate to the router that those many bits make up the network part. As I said, routers are better at doing binary math. They are not humans, right? For us humans, it's easy to see, okay, the first 24 bits. But for a router, it's much easier to do this bitwise arithmetic, right? So it's essentially doing the same thing, right? Okay, now since I didn't show you a meme, hopefully now this meme is making sense to you. The meme on the course website, right? So this is basically wear a mask, and that's your home address, right? It's a restricted address which indicates localhost. Yeah. Okay. Right, so let's move forward now. So the way originally the addresses were assigned was they thought all networks can be of the same size. So back in the 70s, they said, okay, we'll just assume that the first 8 bits of the IP address make up the network, the remaining 24 bits make up the host. What that meant was they could only have 2 to the power 8 networks. So a total of 256 different networks, and each of those networks could have 2 to the power 24 hosts, right? So they thought this is going to be enough. No, they thought there is no way the internet will have more than 256 networks, and how wrong they were, right? Clearly the internet today has many, many, many more networks than 256 different networks. So very quickly they realized this is a problem. So then they said, okay, let's not have this rigid single size of networks, but let's create different classes. So disregard these two. We won't be looking at those two, but for our perspective, they decided networks will be of 3 sizes. So you'll have what are called class A networks, where the first 8 bits make up the network part, the remaining 24 make up the host part. So they range from that. Right? Then class B, which is 16 and 16, and class C, which is 24 and 8. Right? So you had different number of networks in each class, and each network had those many hosts. Right? So you could imagine this to be large, medium, and small in a sense. Right? So if you wanted a large network, you would ask for a class A address. If you wanted a medium-sized network, you ask for a B. If you wanted a small one, you ask for a C, right? So that was the logic, right? But again, here, yes, this was better than not just having one fixed size. But again, this is again too restrictive, right? What if, for example, you wanted slightly more than what a class B could give you, right? So then you either had to ask for 2 class B addresses, or you go for a huge class A address. And in fact, this started to become a problem because many organizations just sort of went for extra large when they didn't really need it. And then a lot of IP addresses were being wasted, because if an organization got a class A address and it was only using 1,000 of those, then it's wasting a huge block of IP addresses just because it felt like buying those, right? So this was again deprecated, and these days we essentially use what is referred to as CIDR, where the number of bits that make up the network part can be any number of bits. So we don't have to stick to 8, 16, and 24. If you want, you could have 9, 10, 11, 22, whatever, right? So it's completely flexible. Why no 0? So those are reserved, right, Tim? So for example, 0.0.0 is a reserved address. So the sum of this convention comes from certain reserved addresses being required, right? So this is just saying, yeah, how do you figure out the type of address? So that's fairly straightforward, right? If you look at this simple flow chart, you can very quickly tell what class of IP address a particular IP address belongs to. So again, elaborating on that point I made, so if an organization requires, say, wants to create 6 internal networks, each of size 30, well, would it have to buy 6 class C addresses, or then it buys a class B and then divides it up? So effectively, people started encountering this problem. So what they then came up with when they were still using these classes was to allow a network to obtain, say, allow an organization to obtain a class A, B, or C address, and then create these subnets that I was talking about, right? So this is sort of telling you a little more about the motivation. So whereby an organization could then create a level of hierarchy within its own network. So what you could then do is, instead of just having the network ID and the host ID, you could take a certain number of bits from the original host ID part and use that to create subnets within your organization. Now, from the point of view of the external internet, they don't need to know about your subnet. So from the point of view of the external internet, your network ID, the first few bits are enough to identify your network. And then within your network, you can create sub-blocks using this subnet ID. So I think this is best described using an example rather than me just talking over bullet points. So this, for example, is a class B address, right? So imagine you're an organization, you have been given a class B address. So these first 16 bits will always be that, and then the last 16 bits can change, right? So what you could potentially do is, let's say you wanted to create 256 sub-blocks within this block, right? Again, just an example, right? So imagine you had 256 departments in your organization and you wanted to give one block of IP addresses to each of those departments. So what you could then do is use these next 8 bits essentially to create different subnets, right? So you would create subnets that go from all zeros right up to all ones here, right? So 256 different subnets. And each of them could then use these 8 bits to assign IP addresses to different devices. So what you have done is created 2 to the power 8 subnets, each of which has 2 to the power 8 IPs, right? So essentially you're using some parts of the original host IDs to create this subnetting, right? So again, a concrete example, let's say a particular company has been given this class C address. So often the entire address that's given to an organization in network jargon is called a site address, right? So this organization has got this, say, class C address. And now within the organization, let's say they have 6 different departments and they want to create 6 blocks of IP addresses. Now, one thing to note here is, since the way these IP addresses are assigned, right, everything is 2 to the power, right? Everything has to be of the order of 2 here when we are looking at specific bits. So notice 6 is not actually a power of 2. So in this example, what you would normally do is you would create 8 blocks, essentially using 3 bits, these 3 bits that you see here, right? Which would give us 8 sub blocks within this larger IP address. Now, of course, in this example, you would only assign 6 of those blocks. You would keep 2. You'd basically not use 2 of them. Right? Oops, sorry. So going back, the way you would do that is, we have been told this is a class C address. So those number of bits make up the network part. So now the question is, from these 8 bits that we have here, how many bits do we need to create those subnets? Since we need to create 8 subnets, 6 essentially, which is effectively 8, which is the nearest power of 2, we would be needing 3 bits to create those subnets, right? So the mask that you would now use in your network is, of course, the first 24 bits, which was already the case with a class C address, and then 3 additional bits. So the mask for your network would now be this internally, right, for the subnets. For your original class C address, that's still the mask. But internally, within your network, when you're creating the subnets, you would be using those 3 additional bits to form the mask. And then within each subnet, you would have 2 to the power 5 addresses. Right? So the way you would assign these addresses is as follows, right? So we've been told the starting address is that 201. That's on the previous slide. So effectively, the first subnet, you would go from 64.0 up to 64.32. So that gives you the first block. Then .32 up to .63, and so on and so forth. I'm not going to map out everything, but hopefully you get the point, right? So this gives us those 8 subnets that go all the way up to .255. And in that example, you would end up using 6 of these. 2 would be left over. Right? Okay, so the addressing we use today, we no longer have these. I mean, for legacy reasons, addresses have originally been assigned as class A, B, and C, but currently we don't use that specific notation anymore. The addresses today are represented in this CIDR notation, which is just more flexible, right? So in class A, B, and C, X could only be 8, 16, and 24. Effectively, now what we have done is we allow X to be anything, right? So it gives you a lot more flexibility to break up a block of IP addresses, right? So in this example, the /X is /23, which means the first 23 bits make up the network part, and then the remaining 9 bits make up the host part, right? So in this network, how many hosts could you potentially have? Anyone? In fact, there is a question on that. So you since we have n bits for the host part, right? You could have 2 to the power n different hosts, right? Which is 512, right? And the range of IP addresses would be all the way from all zeros. So all the 9 bits being all zeros, which is this, and then all the 9 bits being all ones. So if you convert that to decimal, that would be what you get, right? So this is what's referred to as the largest IP address. This is what's referred to as the smallest IP address in this particular block. Now, one thing I missed earlier was the 2 edge addresses are actually reserved addresses. So this address, the first one, is referred to as the network address. So normally you do not actually assign this to an actual device, because this is essentially the address of this network itself, this whole block, right? And this last address, which is where the host bits are all 1, this one, is what's called a broadcast address. So when you want to send a message that needs to be broadcast to all the hosts that are on this network, you would use an address where the host bits are all ones. These 9 bits are all ones. So that's the reason this address is also not assigned to an actual device. So in effect, we have 512 minus 2 actual assignable addresses. The 2 edge addresses are never actually assigned. Okay, those are kind of reserved. There's a question: what would typically drive the decision to create X subnet? So yeah, that goes back to your internal setup, right? So again, hypothetically, let's say UNSW has, again, hypothetically, I don't think this is correct. Let's say UNSW gets a class A address, right? So then UNSW internally, the network designers need to see, okay, how many different departments do we have? How have we actually set up the network? How do we want to allocate these this block of IP addresses to different departments, right? How many do we give to engineering? How many do we give to Uniwide and stuff like that, right? Um, so it's essentially it's driven by the requirements of the organization, right? So it's entirely up to the organization how they create this, right? Why the number of addresses here in each subnet is 32? Well, because if you look at it, this is a class C address. So the first 24 bits were already reserved for the network part and 8 bits for the host part. What we have done is we've taken 3 of the leading bits from this host part to create the subnets. So then we are left with 5 bits that can be used within each subnet. So that's the reason the number of addresses in each subnet is 2 to the power 5, right? Can broadcast address be abused to increase network traffic? Yes, potentially, because anything sent with a broadcast address is being sent to every device on the network, right? So again, yeah, typically most firewalls will be filtering some of this broadcast traffic. So anything that creates all this unnecessary traffic is typically always metered and policed by firewalls. And if they detect things that are anomalous, that will immediately lead to blocking some of the traffic. It may create an alert for the network administrator to have a look at the traffic, right? Okay, so maybe you can answer this question for me now. This should be active already. So how many addresses do you think belong to that particular subnet? Yeah, perfect. So remember here 23 bits of this block make up the network part. So we are left with 9 bits. So 2 to the power 9 would be 512, right? So that's correct. Well done. Okay, so what happens when there are no available host parts? Well, then you need to perhaps look at the allocation again, right? If you run out of IP addresses in that block, you would need to then reassign or maybe get another block or something like that. Essentially, that becomes a question of how do you then adjust the original block of IP addresses itself, right? So this is a little more elaborate example. So here an IP address has been given a class B site address. So that's this one. And it needs, this is an ISP, right? And the ISP has customers with these requirements. So there's one group where it has 64 customers, each needing those many, 128, each needing those many, 128, each needing 64, right? So this, I think, is going back to some of the questions you had, where how do you go about? So this is entirely driven by the requirements, right? How do you create this? So if you were this ISP for this first group, we know that each of them needs 256 addresses, which means we are essentially looking at /24 blocks, because when you use /24, you're left with 8 bits for the host part, and we need 128 of the, no, sorry, 64 of these. So you start off, again, I mean, this is just one way to do things. You could first start allocating the second group. So it's not like there is one specific way to do it. I'm just showing you one way where you would first start off allocating this group, then this group, then this group. You could always do it in a different manner, right? So here we start with the lower end of those blocks, so on and so forth till we get these 64 blocks, which means we have allocated 64 times 256. And then for the second group, we need 128. So this means we should be using /25. And then the remaining 7 bits would be used for the hosts. So then you start off with where you left off. So we are done with, we have allocated addresses up to 63.255 last time. So we start with 64.0, that's the next one. And you keep doing that. In this case, you have 128 different blocks, as you see here. And then for the last one, we need 64, right? So that would mean 2 to the power 6. So this would be in a /26 address. And again, you repeat the same thing, right? So yeah, that's just the final result. So I have a walk through this, and let me know later if you have some questions. This is fairly straightforward. I mean, you just need to be get your head around binary conversion, which is not too bad. I mean, that's fairly straightforward to do. There's a question, wouldn't you have to go /23 because of the 2 edge domains? What would you mean by the edge domains here? And which one were you referring to? I kind of, you mean here? There is no edge domain, right? So within each block, you have the edge addresses. So certainly you wouldn't be assigning these 2 addresses to actual devices, right? So yeah, I mean, here we are talking of just addresses, right? The requirement is not that we have 256 hosts. We were just told this customer needs those many addresses. So we assume the customer knows that they should not be assigning a .0 and .255 to actual devices, right? So this customer would only be actually assigning 254 addresses actually, but they're requesting for those many addresses. So we give them those many addresses. Okay, so now moving on a little further, how does a host itself get the IP address, right? So we've seen, okay, a network administrator creates these blocks. Now within a particular subnet, how does so let's say in this subnet, how does one host get a particular IP address that belongs to that subnet? So that's the first question. And then the second question is, again, going back to that example, mainly looking at it from outside, from the organization as a whole. How does this original organization, how does the ISP itself get this block in the first place, right? So we'll answer those 2 questions now. For the first question, how does a host get the IP address? There are 2 options. One is where you could hard code it yourself. This requires, of course, super user privileges, and clearly this is not scalable. So this is not really practical to do. A more practical thing to do is to use a protocol called DHCP. So this is a specific protocol that is designed for end hosts to dynamically request IP addresses from a particular server. And this is a plug and play protocol. And this is the most widely used protocol for obtaining IP addresses, right? So the goal here is, okay, you allow any host that is authorized to join your network. Now, mind you, DHCP itself doesn't do authentication. So for example, when, eventually when you come to campus and you're connecting to Uniwide, you may remember, if you've been here, first time you set it up, you had to set up your ZID and ZPass, right, to allow you authentication. So this discussion here assumes you've already done the authentication. So I'm not going to talk about authentication because that's not strictly part of the DHCP protocol itself. This just focuses on, you have an authenticated host. Now it needs to obtain an IP address, right? So DHCP allows a host to get this IP address from a specific server, DHCP server. It also allows a lot of other things in that it can, once you have obtained an IP address, you can continue to use it, essentially renew the lease as it's called. So initially you're given an IP address for a certain duration. If you want to remain online for longer, you can just tell the server, hey, I want to use this for longer. So it renews the lease. And the most important thing is this is all done dynamically, right? So again, here we are relying on, if you may, statistical multiplexing. For example, UNSW has how many? 50,000 students, right? Now, clearly all 50,000 students are not going to be on campus all the time. So strictly speaking, UNSW doesn't need 50,000 IP addresses for its 50,000 students, right? They may have some statistics on how many people are actually on campus at any given time. Let's just say it's, I don't know, I'm just making up 5,000, right? So in practice, they could just use 5,000 or maybe 6,000, over provision a little bit, right? So it's sufficient to have, oh yeah, Tim is saying 2 devices. Yeah, I mean, you get the point, right? So certainly people these days don't just use one device, they use multiple devices. But in any case, the point being that you, by having this DHCP server do the allocation, we can actually support a larger set of users by using a smaller block of IP addresses, because at any given time, only a subset of them will be online, right? So this also allows reuse, and it's a very simple way to join a network, right? So a device comes in, it runs DHCP, gets an IP address, it disconnects, it could move to a different part of the campus and then obtain a different IP address or retain the same IP address depending on how things are set up. So it gives a lot of flexibility essentially for devices to join and get IP addresses. The actual protocol goes through 4 steps, and we'll look at those right now. So typically there's one or more DHCP servers on a particular network. So they are very often, they're just co-located in the router. In other words, the router itself is implementing a DHCP server software, right? That way it services all the subnets that it's connected to. So when a device comes in, it needs to obtain a DHCP, sorry, an IP address. And as I noted earlier, we assume the device already has done authentication, right? So that's not part of this. So what does it then do? Well, it basically asks, hey, is there a DHCP server out there? Now, of course, it's not verbally going to ask that. It sends a packet. So it's, the packet is referred to as a DHCP discover packet. One thing you'll notice is DHCP always uses port 67 and 68. So the sending client always uses 68. The server always uses 67. So those are well-defined port numbers. Since this is a broadcast message, and since this arriving client doesn't even know which subnet it's belonging to, it uses the universal broadcast address, which is effectively all ones. So this is like literally shouting on the network saying, hey, I want an IP address, right? Basically, that's this is referred to as your address. So that's the address that will be eventually assigned. Right now, it's all zeros. The transaction ID is just some ID, which allows the client to match up the response that comes back. right? It's just some random number. The server, when it listens to this, will shout back saying, hey, I'm a DHCP server. Here's an IP address that you may use, right? Now notice here, the destination address is still broadcast because this client has not yet got an IP address. So there is no way for the server to unicast to directly send something to this client because the client doesn't yet have an IP address. So it has to shout. Essentially, again, it's a complete broadcast, as you see there. And this is the address it's offering to this client. And then there's a lifetime. So basically saying that you can use this address for that duration. Now, potentially, the client could be potentially, and in fact, almost always, there are multiple DHCP servers. Again, typically, when we are relying on servers to do something important, the normal convention is to have redundancy, right? You've already seen that with DNS. We don't just have one authoritative DNS server. We have at least a primary, a secondary, if not more. So the same thing with DHCP. You would normally have multiple DHCP servers. So sometimes a client will receive multiple offers, right? So in this picture, I'm just showing you one offer. The client may also receive another offer from another server, right? And now the client has to then pick one, essentially. So then it's saying, okay, I would like to use this IP address, and it's telling that to this server. Now notice still the source address it's basically blank. All zeros is just a blank address. It's a special address basically. So even though it's going to start using this address, this has not yet been confirmed. So it cannot yet use this address. So the source address is still all zeros. You might ask, why does it now shout? Why couldn't it send this directly back to the DHCP server now that it knows its IP address? Well, the reason for shouting is since it's responding to one server, the hope is that the other server also hears this. And so this other server will know that he was rejected, right? And that this client decided to go with the offer made by this server. So that's the reason the request is still broadcast, just so that potentially other servers may know that this client went with this. So this server can release its offer. It doesn't need to keep waiting, right? Then we have, that's just the lifetime. And then we have the final ACK. And only from this point on can the client start using the address. So even this last ACK is still broadcast because until the client receives this ACK, it cannot start using that address, right? So at this point, the client now has confirmed this address, can start using it from that point on, right? There are some questions, I'll come to that. I just want to highlight that, so this is a 4-step process. Now, the first time a client obtains an IP address, it goes through that whole 4-step process. But from that point on, right, say if the client has remembered the previous address it got from this server, let's say you came to UNSW, you got an IP address, you went home, you came back. Now your machine detected that it's connected to the UNSW network. It remembers last time you were using an IP address. So the client could directly start with this step saying, I want to use this previously assigned IP address. If the server sees that this address that was given to the client was not used before, it could just send back an ACK right there. And then the client only needs to go through these 2 steps, right? So those first 2 steps are optional. Essentially, that's what you would do the first time on. Of course, sometimes the ACK would not come and then you would have to, I forget the exact mechanism, but I presume there's a way for the server to convey that, or maybe it provides another offer. I forget that process where it's rejecting a previous offer essentially. But the protocol should have something in there to determine that. So let me look at a question. How come it uses a hard-coded source port? Which I think that's the standard for DHCP to use. I'm just trying to think, why might this be hard-coded? I mean, strictly speaking, it could potentially be any port, right? Because it's been conveyed here. So the server would know what port it's needed. I'll need to check that. I'm not 100% sure why it's hard coded. If you have two end users requesting IP addresses pretty much simultaneously, could one take an offer that was intended for the other? No, because there's this transaction ID, right, which is unique. So if another client has requested something, it's unlikely it's going to choose the same transaction ID, right? So the server would never offer the same IP address simultaneously to different hosts. And they may also use MAC filtering. Yes, you're correct. Sometimes some networks do that. If there are multiple DHCP servers, do they synchronize their available IPs, or do they offer non-overlapping IP addresses? I would think they would perhaps be offering non-overlapping IP addresses. Otherwise, there'll be collisions, right? So there must be some heuristics whereby maybe this guy starts at the higher end, this guy starts at the lower end of the IP addresses, of some sort of heuristics they could come up with, right? Okay, now DHCP not only assigns an IP address, it will also return a lot of other important information that can be useful. So things like the address of the first hop router that's to be used for the client, the addresses of the local DNS servers that are on the network, usually the primary and the secondary, the network mask, which I talked about, which allows the host, as you will see later, that will be useful for the host to, when it's sending a packet, it can quickly figure out if the destination is on the same network or not, right? So this is again showing you the same example and just clarifying that DHCP is actually running on top of UDP, right? So when a machine comes in for the first time, it creates this DHCP message that is encapsulated in a UDP segment, and then it gets pushed out. The frame is broadcast, as you see there, and then it's de-encapsulated, and then the response comes back, right? And so that's just showing you on the layering. And at this point, the client would know its own IP address, the DNS servers, and the IP address of the first hop route. The other question was, how does the network itself get an IP address, right? So this is basically a hierarchical process, right? So each organization is sort of subscribing to a higher tier organization in the hierarchy of the internet, right? So if you're an organization, you would obtain a block of IP addresses from your ISP, and the ISP would be essentially given a larger block, and the ISP would be breaking up that larger block into smaller blocks, right? So here you see a /20 address has been broken down into 8/23 addresses, right? Again, this is a very simplistic example. An ISP probably has much more complicated requirements than something simple like that, right? But effectively, each organization gets a block from the ISP. A tier 3 ISP gets a block of IP addresses from tier 1, and so on and so forth, right? And so this, again, I think Tim had asked a question earlier how this is done. So it's kind of done in a hierarchical manner, right? So imagine this is a tier 1 ISP. So it's creating these smaller blocks and then assigning them to, say, a lower tier ISP that's creating smaller blocks, and this can happen on and on. And again, there is no standard fixed way to do this allocation. It pretty much depends on the requirements of the client. Essentially, the client is the one who's requesting the address, right? And then when you go into an individual organization, again, it depends on the specific requirements of that organization. Now, the good thing about having these hierarchies is, as you'll see later when we talk about routing protocols are effectively advertising blocks of IP addresses. So by having this hierarchy, we can actually aggregate multiple addresses. And then here, for example, you have this ISP. This ISP has, say, 8/23 addresses. So when this ISP is advertising the IP addresses that it owns, rather than sending out advertisements for 8 different organizations, it can advertise for this larger block /20. So it only sends one advertisement rather than 8 advertisements, right? So this way, when any other routers on the internet wants to send data to any of these organizations, they would send it this way. And then this ISP itself can figure out where it should go to, right? Because it knows the specific subblocks. But for the rest of the internet, they don't really need to know all these subblocks. They only need to know this larger blocks. Right? So for a same IP address, it will refer to a different host depending on /x. No, it's not the same IP address, right? These are blocks of IP addresses. This is not one address, right? So this is a /20, which means this is effectively an advertisement for 2 to the 12 hosts. It's not a single IP address we are advertising, right? Would the allocations to the top tier ISPs be loosely based on the size of the population? Possibly, yes. But again, there's a lot of, there's some statistical multiplexing at play, right? So, even your ISP, for example, it's unlikely that, there's some sharing of IP addresses even at that level, right? But yeah, roughly there should be some correlation, I would think, to the actual population size that's being served, right? Because typically each one of us at least needs one IP address. And then as you'll see later, NAT helps because by having this private IP addresses within our homes, we can effectively have one public IP address and then as many private IP addresses as we want. So we'll talk about that next week. Right? Okay, one other advantage of having this hierarchies is if an organization moves, right? So if you see this picture, let's say this organization wants to move, it's unhappy with this ISP, and let's say it wants to take its block of IP addresses and join this different ISP, right? Now this is entirely possible because what can happen now is this other ISP, so it was originally advertising its block. This is still advertising its block. What this ISP now can do is, in addition to that, it can start advertising this organization one block, right? Which was originally part of this. So you might wonder how this will work, right? Because this address was originally part of this larger address, but now we have taken it out and we've started advertising it through this path. So is this going to create a problem? And the way the routers do the matching, actually this will not create a problem. So let me explain why. Because what has effectively happened is we have this larger block that was being advertised by the original ISP. And now we have this customer who has moved to this other ISP. And this ISP is now advertising this more specific block, right? The /23 block. So what routers do is they use what's referred to as the longest prefix match. So when they're doing the matching within their routing table, in this instance, for example, let's say a router in the internet has an entry for this block and it has an entry for this larger block, right? So if it gets an IP address that belongs to this block, it's actually going to match the larger /20 block, and it's also going to match the /23 block. So it's actually going to get two blocks of IP address, two matches, right? Because that IP address is clearly matches the original larger block, but it also matches this more specific block. However, this match is longer in that 23 bits will match, whereas here only 20 bits will match. So by using this notion of longest prefix match, this will no longer be an issue, because in this case, packets that are headed to this network will get a match for this link, and packets that are headed to any of the other networks will get a match here, because they will not match any of these, this specific block here, right? So that's the beauty of longest prefix match. So this is just sort of explaining how this longest prefix match works effectively, right? So these are the entries within this forwarding table. So this is a /21 entry, sorry, /19, my bad, /19. That says, oh no, I think I was right. 16 plus 5, right? Yeah, so that's /21. That's a /24. This is a /21 as well, right? So when a packet comes in, and let's say that's the address, by looking at this, can you tell me which of these outgoing links would this packet go to? Some of you are saying 0. So we can walk through this, right? So try to do a match here. So of course, the first 16 bits are all the same, so we kind of can ignore them. We kind of just focus on this block here. And you'll notice this matches only this one. It doesn't match this, and it doesn't match this. So for this one, it is indeed interface 0. Now, how about this one, the second packet? So notice again here, we don't need to worry about the first two blocks. Let's just focus on this one. So this is 00011, 000. So we get a match here, and we also get a match here, right? So we've got two matches. But remember, we are looking for the longest, that is a more specific match. And clearly this is a longer match because the first 24 bits match. So the answer here would indeed be 1. Right? So yeah, well done. So there was a question, and I think James posted something about IP addresses and how they're assigned. So there is some, the way the IP addresses have been historically assigned, there is some geographical significance, though this is not necessarily always accurate. There might be some inaccuracies, but it gives you a fair approximation. So this is something you may try. Go into this website and put in your current IP address and see if you get a reasonable match for your location, right? And now going one step higher, how does the ISP itself get a block of IP addresses? So there's actually a global organization called ICANN. So this is the Internet Corporation for Assigned Names and Numbers. So this is controlling IP address allocations all across the world. And in fact, they've created subdivisions for different parts of the world. So in Australia, for example, we fall under APNIC that controls the IP address for Asia Pacific. So if you set up a new ISP, you will need to go to APNIC and get a block of IP addresses from APNIC. Now the problem is IP addresses have run out. So currently, I think APNIC doesn't actually have any spare IP addresses. In fact, there's a market. I think you can actually trade a block of IP addresses for a fairly large amount these days, right? Because most IP addresses have actually been exhausted. So we'll talk a little bit about that and the implications and the reason to move to IPv6 next week. So this is again walking you through a made up example. This is not a true example. So let's say ICANN gives APNIC several /8 addresses. AppNic gives Telstra one specific block of /8. And then say Telstra gives UNSW a sub block within that, say a /16. So that means that those 16 bits are always the same for any UNSW address. And then UNSW could give CSC, say a /24 block, which would mean those 24 bits are always the same for any machine in CSC. And let's say that's my specific IP, right? So that's sort of showing you the entire hierarchy right up to the top. Okay, I think I went on a little too long. Sorry about that. But I think let's call it a day. I'll hang around if there's any questions. If not, have a great week. Do remember to keep working on your assignment. The assignment consults are running, so certainly avail of those if you need. And we'll have your midterms marked by Monday. I'll probably not release it before the lecture because that's already too early. But later in the day on Monday, you should expect to see the midterm results. So see you all Monday and have a great week. Bye-bye.